So in this video, I want to go over the Claisen condensation, but first let's remind ourselves of the Aldol reaction. We know we can have these Aldol reactions where we know these carbons that are adjacent to these carbonyls, these carbonyl carbons, so we know these carbons can act as nucleophiles. We know they have hydrogens. For example, this carbon, we know it has a hydrogen that we can deprotonate. And when we deprotonate, these electrons in this bond fall on this carbon. And when we do that, we create this carbon anion. And because this carbon anion is adjacent to this carbonyl, we know there's resonance. There's resonance stabilizing this carbon anion. So therefore, we can create this carbon anion, which can act as a nucleophile. And we know these carbonyl carbons can act as electrophiles. We know they're double bonded to this very electronegative oxygen atom, pulling electron density. It's stealing electron density, creating an electron deficiency on this carbon, which therefore can act as a electrophile. So now we can know we have this kind of Aldol reaction where this nucleophile nucleophilically attacks this electrophile. And when we do that, we would form this product. Where again, we formed a bond, so that bond would be represented by this bond. And when we do that, we push these pi electrons up onto this oxygen, creating this tetrahedral intermediate. However, we know normally these tetrahedral intermediates are unstable. So normally they collapse where these lone pairs would fall down, forming a double bond. But we know when we do that, we would have to break one of these bonds. Maybe we would have to break this bond. Or maybe we would break this bond. Or we would break this bond. However, notice that's not reasonable. We can't do that because if these electrons fell down forming that double bond, which bond would we break? Would we break this bond or this bond? Or maybe this bond? Well, we realize none of these are good leaving groups. We know this carbon anion wouldn't be a good leaving group. We know this hydride breaking this bond and these electrons falling on this hydrogen would be a terrible leaving group. And again, this also wouldn't be the best leaving group. So we're kind of stuck. Well, once we've attacked, we're stuck with this tetrahedral intermediate because we don't have any good potential leaving groups. So we're stuck with this, so therefore we're stuck protonating this oxygen. So then we protonate this oxygen, creating the alcohol. And this is referred to as the Aldol condensation. So this is an Aldol condensation. We learned about this in the previous video. But we know these Aldol condensations are always followed by dehydration reactions, where we know this hydrogen that's essentially adjacent to the carbonyl, we know we deprotonate it with these electrons falling down, forming a double bond. And when we do that, we break this bond with these electrons falling on the hydroxide. And when we do that, we would essentially go through a simple elimination reaction, forming this dehydrated product. And we know this is the aldol. When we go to this, that's an aldol condensation, and it's always followed by this dehydration reaction. So we learned about that in the previous video. But now let's do a different example. Let's do a similar situation, where again, we know this carbon can act as a nucleophile, because again, we deprotonate this hydrogen, creating the carbon anion nucleophile, which is stabilized by resonance, so we can form this carbon nucleophile. And we know this carbon can act as an electrophile. We've just explained that. So we know we can nucleophilically attack this electrophile, forming a bond, and when we do that, we push these pi electrons up onto the oxygen. And we know when we do that, we form this product, where again, we formed a bond, so that bond is represented here, but when we did that, we push these pi electrons up onto this oxygen, creating this tetrahedral intermediate. However, we know when we were doing the Aldol reaction, we were stuck with this tetrahedral intermediate. We didn't have any good leaving groups. So therefore, this tetrahedral intermediate couldn't collapse where the electrons fell down, forming a double bond, breaking one of these bonds. We know we couldn't do that because we didn't have any potential leaving groups. We didn't have any good candidates for leaving groups. So we were stuck with this tetrahedral intermediate, so we had to protonate this oxygen, creating the alcohol. However, with this Claisen condensation, it's a similar mechanism. However, once we form this tetrahedral intermediate, we do have a good leaving group. This chlorine is a good leaving group. This can act as a good leaving group. So we're not stuck with this tetrahedral intermediate. The electrons can fall down, forming a double bond, breaking this bond with these electrons falling on this chlorine, because this chlorine is a good leaving group. So that's the difference. When you don't have a good leaving group, you're stuck with the Aldol condensation. However, when you do have a good leaving group, you can collapse the tetrahedral intermediate, collapsing, breaking this bond, having this acting as a leaving group. So if we did that, we would form this product. So that's the difference. The electrons can fall down, forming that double bond, breaking this bond. These electrons fall on this chlorine, and then the chlorine just acts as a leaving group and just floats away as a chloride ion. So this is referred to as a Claisen condensation. And notice the reaction's parallel. They're pretty similar. The only difference is once we attack, this tetrahedral intermediate is stuck. We don't have a good leaving group, so we're stuck. We're stuck with this tetrahedral intermediate, so we have to rely on protonating it, creating the alcohol. However, this tetrahedral intermediate, once we attack forming this tetrahedral intermediate, we do have a good leaving group. This chlorine is a good leaving group, so we can collapse the tetrahedral intermediate, allowing that double bond to form, this double bond to form, breaking this bond with these electrons following this chlorine, forming this Claisen condensation product. So now let's do a different example. So let's say we have a solution of these two compounds. We know we could have a mixture of lots of different reactions. We could have, because again, we learned in the Aldol reaction how to determine and identify the nucleophiles. We know this carbon can act as a nucleophile, because when we deprotonate this hydrogen, we form this carbon anion, which is stabilized by resonance. It's adjacent to this carbonyl, so we know we have resonance stabilizing this carbon anion. So this carbon can act as a nucleophile. It's a carbon anion. We know this carbon isn't a nucleophile. Why? Because if we deprotonate this hydrogen, we form this carbon anion, which isn't stabilized by resonance. There's no resonance stabilizing this carbon anion. So we can't form that carbon anion, so this carbon can't act as a nucleophile. And again, this carbon can act as a nucleophile because it's adjacent to a carbonyl. We can deprotonate this hydrogen, forming this carbon anion, and this can act as a nucleophile. So we know these are the two potential nucleophiles, and these are the two potential electrophiles. So we could have a mixture of reactions. Maybe this nucleophile attacks this electrophile. And if we did that, we know we would form a bond here, pushing these pi electrons up onto the oxygen, forming this product. Where again, we form a bond, we form this bond, pushing these electrons up, creating this oxygen anion. So that's one potential product. That's one potential reaction. And again, if we did that, we would essentially form this compound, which again, we know this compound, when we attack pushing these electrons up, forming this compound, with this compound, we do have a potential leaving group. We know we attacked forming this tetrahedral intermediate, but we're not stuck with this tetrahedral intermediate because we do have a good leaving group. So when we have this kind of reaction, this kind of carbon that's adjacent to a carbonyl acting as a nucleophile, attacking one of these carbonyls, forming this tetrahedral intermediate, but this time we do have a good leaving group. So therefore, this tetrahedral intermediate can collapse. The electrons fall down, forming a double bond, breaking this bond, because this can act as a good leaving group. We know this carbon isn't a good leaving group, and this carbon isn't a good leaving group, but this oxygen is a decent leaving group. So we were not stuck with the tetrahedral intermediate. The electrons can fall down, forming a double bond, breaking this bond with these electrons falling on this guy, forming this product. So again, this is a Claisen condensation. However, we could have a different reaction. Maybe this carbon nucleophile attacks this carbon electrophile. And if we did that, we would form this product, where again, this carbon nucleophile attacks this carbon electrophile. So we form a bond, so that bond would be represented by this bond. And when we do that, we push these pi electrons up onto this oxygen. So when we do that, we would form this tetrahedral intermediate. But in this example, we're stuck with this tetrahedral intermediate. We don't have any good leaving groups. We know if these electrons were to fall down forming a double bond, we would have to break one of these bonds, maybe break this bond, or break this bond, or break this bond. But none of these are good candidates because none of these are good leaving groups. Hydrogen is a terrible leaving group. These electrons falling on this hydrogen, that's a terrible idea. This carbon is a terrible leaving group, and this carbon isn't a good leaving group. So we're stuck with this tetrahedral intermediate, so we have to rely on protonating this oxygen intermediate. So when we do that, we would form this product. And again, so we're stuck protonating this guy, forming this aldol reaction. And then again, we know whenever we have an aldol reaction, it's followed by dehydration reaction with these electrons and then these electrons falling on this guy. And we talked about this in the aldol video, forming this product, forming this dehydration reaction. But the point is, we could have a mixture of reactions. If this carbon attacks this guy, we would form this product, which would be an aldol reaction because we have no good leaving groups. So we're stuck with this tetrahedral intermediate, so we're stuck with protonating this guy, forming the alcohol. So this would be an aldol reaction because we don't have a good leaving group with the tetrahedral intermediate. However, if this electron attacked this guy, pushing these electrons up, forming this tetrahedral intermediate, we do have a good leaving group. We do have a good candidate for a leaving group, so it can act as a leaving group. These electrons fall down, and then these electrons fall on this guy, forming this product. So again, this is a Claisen. This particular reaction would be a Claisen condensation, while this particular reaction would be an aldol reaction. And the difference is these tetrahedral intermediates and if there's a good leaving group or not. If we have a good leaving group, we go through the Claisen condensation. If we don't have a good leaving group, we're stuck, so we have to protonate this guy going through the aldol reaction.